14 miles southeast of the settlement of Ruby, Alaska, the terrain dictates the limits of any heavy engineering operation. The ground around the wreck site was defined by tundra, wet lowlands, and scattered surface water, creating a barrier to ordinary heavy overland recovery. Ruby itself had local routes, river access, and seasonal transport options, but the last stretch to the aircraft remained the controlling problem. In this isolated recovery environment, distance was not measured just in miles, but in the operational penalty of moving heavy equipment across terrain with limited load-bearing margin. This strict geographical boundary defines the logistical parameters for an extraction mission targeting a specific high-value aviation artifact. The objective is not a conventional salvage effort, it is a highly specialized aerial component harvest. The target is the Boeing B-17F Flying Fortress, United States Army Air Forces, serial number 42-30681. This specific bomber was an asset assigned to Ladd Army Airfield near Fairbanks, Alaska. Its operational profile involved cold weather testing and utility transport duties across a region known for extreme environmental variables. When the airframe was lost over the wilderness, those same conditions removed it from standard recovery channels and turned access, not value, into the controlling obstacle. For decades, the airframe remained a remote Alaskan wreck rather than a practical recovery target. Public summaries are not perfectly consistent on whether 1996 marked the first rediscovery or the first major recovery effort. What is documented is that Gary Larkin salvaged the tail and fuselage during 1996 after the aircraft had remained in place for decades. The site's survival confirmed the bomber's value, but it also forced a different operational logic. The recovery team had to approach the wreckage as a modular problem, focusing on viable structural sections rather than attempting to move a complete, intact airframe across the tundra. That constraint made aerial lifting the practical solution, and every lift carried strict weight and balance limits. The next task was to identify which surviving sections had enough structural value to justify a lift. Every piece of heavy equipment, every tool, and every member of the recovery team had to be flown into the site. The footprint of the expedition was entirely governed by the payload capacities of available helicopters and the short time frame allowed by weather conditions. The 14-mile gap between the wreckage and the nearest staging area acted as a strict filter, determining exactly how the operation would be sequenced. Gary Larkins and his team were forced to evaluate the wreckage not just as a historical artifact, but as a series of distinct engineering payloads. The survival of the airframe over 53 years provided the opportunity for extraction, but the location demanded absolute precision in how that extraction would be executed. The team had to prepare for a multi-stage process, breaking down the massive bomber into manageable nodes that could be lifted vertically from the marshy ground. The physical reality of the site dictated every operational decision, forcing the recovery effort to adapt to the absolute limitations of the Alaskan wilderness. How does a heavy bomber structure remain viable enough for extraction after more than half a century exposed on the Alaskan tundra? On September 25, 1943, a mechanical failure presented an irreversible trade-off boundary. The B-17 aircraft could no longer be treated as a reliable machine over the remote interior wilderness. Public accident summaries state that the crew bailed out before the crash. One man died while the others survived and were later rescued. That decision removed the crew from the final phase of flight, leaving the bomber to descend without further human control. The exact altitude, control positions, airspeed, and attitude at impact remain undocumented in the public record. That missing data prevents a precise reconstruction of the uncrewed flight path after the bailout. The condition of the recovered wreckage is consistent with a relatively low-energy ground contact compared with a vertical, high-speed impact, but the exact aerodynamic sequence cannot be stated as fact. The safer conclusion is narrower. The aircraft came down in a way that left major sections recoverable. When the aircraft met the Alaskan surface, terrain became one of the factors that shaped the wreck's survival. The site is described as tundra near Ruby, and a wet or seasonally thawed surface may have helped limit breakup compared with rock, trees, or a hard-prepared surface. But the public record does not document a measured slide path, a uniform load distribution, or a proven cushioning model. The more defensible point is that the crash left enough major structure intact for later recovery. This more limited chain of evidence still matters. Whatever the exact impact mechanics, The wreck did not vanish into small fragments. The tail, fuselage, wings, and other components survived in a condition that later recovery teams considered useful. The bomber's geometry was damaged but not erased. The question was no longer whether anything remained. The question was what strategy could extract usable structure from a remote tundra crash site. In 1996, an operational window opened to address a site that had remained untouched for 53 years. The time elapsed created a distinct structural reality. Instead of degrading into oxidized fragments, the airframe entered a state of suspended decay. The recovery team faced an environment governed by extreme sub-Arctic temperature cycles. This local constraint forced a specific preservation effect on the aluminum monocoque structures. Cold conditions can slow some forms of deterioration, but they do not stop corrosion. Aircraft aluminum still depends on moisture, trapped water, dissimilar metals, contaminants, and the condition of seams and fasteners. The useful point is more careful. The Alaskan environment helped preserve some major sections well enough to justify inspection and recovery. The expedition was dealing with aged aerospace material, not guaranteed structural stock. While the survival of the airframe proved the viability of the recovery, extracting the material required solving the access limitation. The team had to establish a remote logistics chain to move heavy lifting equipment and recovered aircraft components over the roadless wilderness. Moving heavy ground transport vehicles over the marshy terrain was impossible. The expedition had to rely entirely on a rotary wing pipeline, flying every wrench, generator, and lifting strap directly into the staging zone. The absolute load capacity of the available transport helicopters set a strict upper boundary on what could be moved in a single flight. This payload ceiling forced a mandatory operational decision. The team could not rig the entire fuselage for a single massive lift. Before any lift, the crew had to treat each section as an external load, not as ordinary scrap. Weight, balance, secure attachment, and controllability were the governing limits. A load that shifted under a helicopter could begin to oscillate, create hazardous aerodynamic behavior, or force the crew to abandon the lift. The practical requirement was disciplined rigging and conservative load control, with each section prepared so the helicopter could pick it cleanly, test it, and move it without exceeding the aircraft's operating limits. The weight limits dictated the operational logic of component harvesting. The public record supports the broad outcome, not a minute-by-minute lift sequence. Gary Larkins salvaged the tail and fuselage during 1996. The fuselage later went to the Tillamook Air Museum. Arctic warbirds acquired the wings and other components, and Larkins returned in June 2001 to recover additional parts. The recovery, therefore, should be described as a staged component salvage, with exact order, cut lines, and rigging details left unstated unless a field report can confirm them. Once the targeted sections were removed from the crash site, they entered a documented chain of storage and reuse. The recovered wreckage was first stored in Fairbanks. Later, the fuselage went to Tillamook, while wings and other components went to Arctic warbirds. One tail-related assembly followed a different path. Public sources describe the tail section as having landed in a small lake, and Hangar 13 later identifies the tail gun, or stinger assembly, from 42-30681 as part of the Lucky 13 project. The exact depth, condition, and water recovery setup remain unconfirmed in the public record. In 2001, Gary Larkins returned to the Ruby site and recovered additional parts. If any of those pieces had to be taken from the lake, the operation would have required careful rigging, controlled lifting, and conservative handling of a waterlogged aircraft structure. But the public record does not confirm the exact depth, visibility, sediment suction, drainage pauses, or step-by-step hoist procedure. Those details should remain outside the narration unless a recovery log or participant account confirms them. The 2001 expedition added further material to the recovery record, but the surviving sources do not prove that it recovered the final critical node, or that the aircraft footprint had been fully converted into modular cargo. The better documented chain is narrower. Major sections had been recovered, moved into storage, and distributed to restoration projects. With the wilderness recovery complete enough to move selected components onward, a new question emerged. How do compromised historical sections survive long-distance transport? Highway transport introduced an immediate risk constraint to the recovered aluminum geometry. The exact total weight of the harvested aft fuselage section remains unknown. This missing load data required flexible, highly adaptive stabilization solutions before the long-distance transit could safely begin. Once the recovery teams transitioned from wilderness extraction to commercial logistics, the primary threat to the airframe shifted entirely. The static environment of the tundra was replaced by the dynamic hazard of the open road. Moving massive aircraft components on flatbed trailers at highway speeds effectively forces the structures to fly again. The transit generates continuous aerodynamic stress on airframes that are no longer structurally intact. The destination for these heavy payloads was located in the Pacific Northwest. The recovered components were initially shipped to the Tillamook Air Museum in Oregon to support a specific ongoing bomber restoration. The journey required moving the massive aluminum assemblies across a transcontinental highway network. The route involved navigating high mountain passes, changing weather patterns, and continuous road vibrations. The engineering challenge lay in the physical condition of the harvested sections. While the aft fuselage was structurally viable for museum use, it was no longer a sealed aerodynamic envelope. The targeted disassembly process used during the wilderness extraction had exposed internal bulkheads, sheared original skin panels, and left raw, open joints. If the recovery crew placed the fuselage directly onto a flatbed truck without protective measures, 60-mile-per-hour winds would enter these open cavities. This internal pressurization would create severe stress cycles, potentially tearing the thin aluminum skin away from the stringers and destroying the exact geometry the expedition had worked so hard to preserve. Furthermore, the lack of precise weight data for the aft fuselage section meant the transportation crew could not rely on standard payload engineering models. They could not perfectly predict how the section would settle and vibrate on the trailer over thousands of miles of asphalt. Custom wooden cradles were built to support the curved underbelly of the structure. Before the protective layers could be applied, the components had to be transferred from the localized staging zone onto the commercial flatbeds. Cranes hoisted the aft fuselage and lowered it carefully onto the wooden cradles. The rigging team then secured massive nylon straps directly over the primary structural frames, anchoring the aluminum tightly to the steel trailer bed. Only after the load was physically immobilized could the weatherization process begin. To neutralize the aerodynamic hazard, the transport crew would have needed some form of protective stabilization. Shrink wrap is a plausible method for shielding aircraft components from weather and road exposure, but the available public sources do not confirm that it was used on 42-30681. What can be stated safely is that the recovered fuselage and other components had to be supported, restrained, and protected during long-distance movement. The purpose of that protection was straightforward. Open bulkheads, cut edges, exposed ribs, and fragile skin panels could not be treated like ordinary freight. Road vibration, wind, weather, and repeated handling all threatened the surviving geometry. Whether the barrier was shrink wrap, tarping, cradling, or another packaging method, the operational requirement remained the same. Keep the aged aluminum from flexing, tearing, or collecting further damage before it reached the next restoration environment. With the transport phase complete, the recovered material had moved from a wilderness extraction footprint into the aviation restoration network. The protective handling preserved its forensic and structural value, but a separate question remained. How is an isolated tail section integrated into a completely different surviving airframe? The engineering decision did not end with storage. One documented piece from the Alaskan donor, the tailgun or stinger assembly, later became part of the Lucky 13 B-17 restoration project. The available sources support that tail assembly connection. They do not confirm that the harvested aft fuselage from 42-30681 was transferred into Lucky 13. This transfer required evaluating the Stinger not as a static museum exhibit, but as donor material for a rebuilt tailgun position. The donor aircraft 42-30681 had been accepted by the U.S. Army Air Forces on July 8, 1943, and had reached Alaska by September 9, 1943. Decades later, its value was no longer measured in its wartime cost, but in the surviving geometry of one recoverable assembly. The Lucky 13 project required an exact match of stringers, bulkheads, and skin to replace severely damaged sections of its own airframe. Mating two separate aviation structures presents a severe tolerance constraint. A B-17 fuselage is not a simple rigid tube. It is a highly stressed semi-monocoque shell where every individual rivet transfers dynamic load. The engineering team had to ensure that the cross-section of the donor bomber matched the exact factory specifications of the host airframe. Even minor manufacturing variations between different production blocks or assembly plants could create internal stress points. If the bulkheads or longitudinal stringers deviated by even a fraction of an inch, the sections would not lock together. Forcing an imperfect fit would preload the aluminum with internal tension, rendering the donor material useless and endangering the integrity of the host structure. To prepare the 42-30681 aft fuselage for this integration, the restoration team had to reverse the original manufacturing process. They methodically decoupled the original skin panels at the designated splice zone to access the primary skeletal members. This required extracting hundreds of solid core rivets without elongating the original holes in the underlying aluminum frames. If a drill bit slipped and enlarged a rivet hole, the joint would lose its structural rating. The technicians mapped the rivet patterns of the donor aft fuselage, translating the mid-20th century manufacturing tolerances into precise alignment guides. Simultaneously, the tail stinger, holding the complex structural geometry of the aft gunner position, was prepped for identical integration. Any corroded or structurally compromised mounting brackets were carefully drilled out and replaced with newly fabricated aluminum stock that matched the original alloy specification. The execution required the strict application of structural splicing logic. Structural splicing is the engineering process of adapting a harvested aft fuselage section from one bomber into the active restoration of another. Technicians must precisely align the primary load-bearing longerons and shear webs between the two distinct airframes. Once perfectly matched, custom splice plates are riveted across the joint to transfer structural tension and compression seamlessly across the mechanical divide. This method restores the continuous load path of the fuselage without compromising the structural safety of either the donor or the host airframe. Once the splice plates were secured and the new rivets driven into place, the assemblies were permanently united. The documented physical integration of the 42-30681 aft fuselage and tail stinger into the modern Lucky 13 restoration securely links the Alaskan wreck to a current museum project. This physical mating represents the primary anchor proof of the entire extraction operation. The targeted component harvest strategy achieved its exact intended result. The operation successfully bypassed the destroyed portions of the bomber, retrieved the viable aerospace material, and navigated the logistics of moving it across the continent. By precisely mating the recovered aluminum to a new host structure, the operational footprint of the Ruby component harvest remains permanently engineered into the continuous, preserved load path of an active historical artifact.